Welcome back to our lesson practice review. Today we start off our chapter 3 with our lesson 1 practice. To kind of summarize what was going on was really today was focused on the functions that we can create given some sort of situation, and then like what kind of equations we can use with that to help tell us certain pieces of information as we go. So one of the main kind of key things that it tells us about is the idea of a local maximum. So when we look at this graph here, we can kind of see this point right here is something that we consider a local maximum because it's the highest point in this kind of area. If we look at just this area here, it's the highest point. It is not the global maximum because we see that like this arrow is going up forever. And so it's not the highest point in the whole function, but it is the highest point in one area of the function. All right, so let's do some problems here. Problems 1 through 5. Rancher Mar is building a rectangular fence for cows using one side of the barn and 120 feet of fencing for the other three sides. So we're really focused on these three sides here, the left side, the top, and the right side. The table shows one possible combination for the length, width, and enclosed area of the fence. Write two more combinations. So let's first understand kind of what is written already. We have the length, which was 80 feet here, the width, which was 20 feet. And so the issue here is that only adds to 100 feet of fencing when we were told that there's 120 feet of fencing. The reason that we have to think about this is because really there's this other side over here on the left that is also the same width or another 20 feet. And when we add that together, that gives us our total of 120 feet. So you can kind of put a lot of different possibilities here. For example, if I put 100 feet for our length here, that means that there's 20 feet left of fencing. And so when we do this, each of these here has to be the same. So if there's 20 feet and I need to divide that by 2, each of these sides here would be 10. And that would add to our total of 120 feet of fencing. Then we multiply the length times the width here, and that gives us our area, which would be 1,000 square feet. Same idea if we were to do, let's say, 50, a little bit less of a length here. That means that there would be 70 feet left over, and half of 70 is 35. So that would be 35 and 35. And then so all those three should add up to 120. So really all three of these values need to add up 120, and the width here, those need to be the same value. That's kind of the key part. To find the area, I just multiply those together, and I end up getting 1,750 for my area. For number 2, if the length of the fence is X feet. Okay, so we're going back up here. I'm going to erase some of these values up here. Let's use blue. We're going to say that the length, we're going to call X. Write functions to represent the width and the area. So to start with the width here, the width is going to be, remember, our length plus our width plus another width was equal to 120, right? So in that case here, we're going to go ahead and say that it is, again, I want to use X for my length, and then W plus W would be 2W equals 120. And if we were trying to find a function that is equal to our width, we would subtract X from both sides. So that would be 2W equals 120 minus our length, and then divide both sides by 2. So when we do that, we get 120 minus X over 2. So that's going to be my first answer here, because this is now an equation that I've created that represents the width. So if I plug in the length, it will tell me what one of the widths is. And it makes sense that we're dividing by 2 here, because remember, like I was doing up in the first problem, that I said like my length was 50 here, and then I knew there was 70 left over, and then I divided that by 2 because I knew the left and the right side had to be the same. The area, so remember, area is just length times width, so really it's going to be the same thing here, which is my width times my length, which I know is just X because that's what I was given. For number 3, what is the enclosed area of the fence when its length is 42 feet? So when we're doing this one here, we are going to, we have equation here that represents the area, let's go ahead and just plug that in, right? So we have A of, in this case, 42, because I'm plugging in 42 feet. 120 minus 42 over 2 times 42. And now when I kind of simplify this here, 120 minus 42 is 78. And then 78 divided by 2 is 39. And then 39 times 42 is 1,638. And we're going to say that it is square feet as my units for the area when the length is 42. A student wrote a function representing the enclosed area of the fence. Here is the graph. What is a reasonable domain for this function? So when we look at this equation here, again, my output of this is the area, where we see that my input is the length here. And so when I'm doing this, the domain represents the x value. So what is the possible length of the fence? And again, really, we're not going to ever have a negative area, right? And we only have 120 feet of fencing. And so the minimum length that it could be is a little bit greater than 0. And it has to be a little bit less than 120 because, again, we have to have some sort of width there. So our x value could be anywhere between 0 and 120. If we had it, closer to 0, then our width would be really big. And if we had it closer to 120, then our width would be really small. Select all the true statements about the fence that encloses the greatest area. So looks like this here is the greatest area here. And it looks to me that this point, or this coordinate here, kind of lands at 60 and what was that, 15, 16, 17, 1800. So the length is 60 feet. Yep, we just said that right here. The length is 120 feet. No, it can't be two of those at the same time. The width is 30 feet, and then the width is 60 feet. Okay, I don't know that just yet. Let's do E here. The area is 1800. I would agree that E is true, and remember that it's length times width equals the area. So to find the width, I would just divide both sides by 60, and I would end up getting my width, which is 30. So this one here, my three answers are A, C, and E. Problem 6 through 9. Omari wants to make a box by cutting out corners from a rectangular piece of cardboard and folding up the sides. The cardboard measures 20 centimeters by 28 centimeters. So we see the picture on the right here to kind of represent that. For number 6, what is the volume of the box when the cutout length is 2 centimeters? So that means this is 2, which means that this is also going to be 2. And when I'm doing this here, I really just need it seems to me like these are making squares would be my guess. And so when I'm doing this, all these little values here are 2, which means that to find this inside value, which is important, I'm subtracting 4. So that would be 24. I'm subtracting 4 from this, which would give me, 16? So then my box here, my height is going to be 2 centimeters, right? Because when I fold this up, this will kind of be the height of the box here. So I'm going to do 24 times 16 times 2. If I do 24 times 16 times 2, I end up getting 768. And we're going to call this unit cubic centimeters because we are doing volume and no longer just square feet, right, in area. Number 7, write a function to represent the volume of the box where x represents the cutout length. Okay, so I'm erasing all this because it's no longer 2. We don't necessarily know what it is. We're going to call that cutout length x, and we are going to be trying to multiply, a couple different things together. So first of all, we have our height, which we know is just x, right? Because that's whatever this value is going to be. That's going to be the height of our box. Then the length here would be, let's say, 28 minus x minus another x. So 28 minus 2x, because I'm subtracting both of those to get my now length. And then my width here would be the same idea, but it's 20. and then we're subtracting x and subtracting x again. So 20 minus 2x. And so you can multiply it all together if you wanted to get kind of our cubic function, or you could leave it as this factored form here. Number 8, here is a graph of a student's function for the box volume. Approximate the greatest possible volume here. So in this one here, we see the volume is our output, the input is our cutout length. And so when we look at this, again, when we look at this to make sense here, is that our cutout length, when we're seeing kind of all these pieces on the graph here, our cutout length x here is limited by this right side because it's 20 centimeters, right? So if I was going to cut out, 12 centimeters, well, then this would be 12 and this would be 12, which would be 24, which is bigger than the actual box. So we can't do that, right? So it limits us, saying like the highest possible would be, 10, which is why we see when we look at this graph here, this point right here, because we can't do that. We can't get this negative value here. So really our cutout value, I'm kind of answering number 9 here, but what is a reasonable domain for this function? Well, it's got to be from 0 to 10. And so really all this other stuff on the right side doesn't matter. That's not going to happen because we're not going to have a cutout length greater than 10. And so really I'm focusing on this kind of, it's not a parabola, but kind of looks that general shape here, this curve. And it's asking us for the greatest possible volume while we're looking for this highest point here. And so that kind of lands somewhere in between 900 and 1,000. I'll probably call it like 970 as our possible, cubic centimeters for an answer. And then again, number 9, what is a reasonable domain for this function? As I already stated, it's from 0 to 10. All right, for our spiral review, solve the equation 5x squared minus 3x plus 7 equals 0. I could go ahead and try to factor this one first. So in this one, in my box here, I got first term, first box, last term, last box. Oh, I already got my x here, my fault. And then I'm breaking up negative 3x into two things that multiply to 35x squared. As I go through all the factors of 35, it's got to be positive, and I can't see anything that would actually multiply to that top that adds to the bottom there. And so what that means is that this is unfactorable. I cannot factor this to solve. And when I try factoring and it doesn't work, my fallback here is a couple different things. I could do completing the square, or I could do my quadratic formula. I'm going to go ahead and throw it into the quadratic formula to get that as my practice. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So when I do this, I'm going to start simplifying some pieces here. 4 times 5 is 20, and 20 times 7 is 140 over 10. Inside that square root, I'm now subtracting these to get negative 131 over 10. And the only real thing I can do to kind of simplify this a little bit more is to get rid of that negative inside the square root. We know that that's going to then become I on the outside, all over 10. Number 11, rewrite the expression in the form a plus bi. So in this one, I'm going to use my trusty box. Negative 7i plus 8, negative 11 plus 2i. And I start multiplying this out. This becomes positive 77i, negative 88, negative 14i squared, and 16i. And so when I add these together, I end up getting 93i. And then remember that this I squared just makes it a negative 1. So this ends up becoming just a positive 14. Positive 14 minus 88 is just a negative 74. And so to write this all in one color to not confuse people, negative 74 plus 93i is now in the form a plus bi. That wraps up our first lesson practice for chapter 3. Next up is 3.02 to continue talking about these different types of functions.